Hi everybody, today we are learning about applications of the dot product and the cross product. So we've already gone into quite a bit of detail about what these are, and you've probably been asking questions about, well, what are these actually used for? What do they do? So this class kind of will help answer some of those questions and how they're used in physical problems and other type of problems that come up in math. So we're going to go through basically something called work, and then the area of a parallelogram and torque. Those are the three main applications we're talking about today. So first, let's talk about work. So work is when a force acts on an object to move it from one place to another. So think about, pushing on a rock or pulling a wagon. But the key is that work has only occurred if there is force, displacement, and cause, all three elements. So in order for force to qualify as work, there must be displacement, so it moving, and the force must actually be the thing causing that displacement. So a horse pulling a plow through a field. Okay, so there is displacement, the plow is being moved, and the force of the horse pulling it is actually causing that displacement. Or a father pushing a grocery cart through a store, a student lifting a backpack. Okay, all of these involve displacement and that the force is causing the displacement. So these 4 questions about is this work? Okay, so a teacher applies force to a wall and becomes exhausted. Well, no, this is not work because the wall is not being displaced. Or what about a book falls off the table and free falls to the ground? So yes, this is work because there is a force of gravity that is acting on the book, which causes it to be displaced in a downward direction. Okay, so then what about, this was the tricky one. A waiter carries a tray full of meals above his head by one arm straight across the room at a constant speed. So no, this actually isn't work. There is force. Okay, the waiter is pushing up on the tray, and there's displacement. The tray is moved horizontally, but the force of holding it up is not causing the displacement. So to cause displacement, there must be a component of force in the direction of the displacement. Okay, so some of the force must be going that way. But if they're holding it straight and they're at perpendiculars to each other, there is no work. Finally, a rocket accelerates through space. Yes, this is force. Yes, this is work. There is a force. The expelled gases push on the rocket, which causes the rocket to be displaced through space. So finally, we get to the mathematical definition of this. So work is defined as the product of the distance of displacement and the component of the force along that displacement. Okay, so if this is some theta here, so if this is the force acting on the object and the object is going from O to A, then the work is the multiplication of how far OA is multiplied by how much of this force is going in the same direction as OA. So that is actually ON, which is the scalar projection of the force along the line that the displacement is actually happening. So OB here, so OB represents a constant force, which we'll call little f, acting on an object at O, so that the object moves from O to A. So then the distance that the object moves is the magnitude of vector O. Sorry, that's supposed to be A. OA, okay? And that, we call that the displacement. Okay, I'm just gonna make sure that you know that that's A. That looks really OA. And then ON we can find by doing the magnitude of the force times cos theta. All right, this is just SOHCAHTOA rearranged to get us the length of ON. And that is also the scalar projection of the force onto the vector. So again, it's just how long is this object moving? What's the distance in meters? Okay, and then what is the component of the force? So the product of that is work, and work is measured in joules. So work is equal to the magnitude of the force times cos theta. So that is the scalar, the horizontal component of the force, times OA. Okay, so that is the displacement in the direction. Okay, so this is actually equal to the force dotted with S. Okay, where S is the displacement of the object. Okay, so this is force dotted with displacement, but this is usually what we will use. Okay, so just so you know, this is measured in joules, which is a capital J. Okay, and then you have, like I said, the horizontal component of the force multiplied the distance of displacement. So that is the dot product. Okay. Where OA is equal to S. So OA could also be defined as the S vector. Okay, so let's talk a little bit more about work because the textbook doesn't go into quite as much detail, but I have found this is confusing, so I'm going to add this in. So a force acts in this situation, the direction and the force are acting together. So a force acts rightward upon an object as it is displaced rightward. In such an instance, the force vector and the displacement vector are in the same direction. Thus, the angle between the force and displacement is 0 degrees. Cos theta equals 0. Cos 0 equals 1. So the work is just the product of the two vectors. So imagine that all of the force is only going in one direction and this displacement is going in that direction. So you're just multiplying the force times the displacement. Okay, now if a force is acting leftward on an object that is displaced rightward, then they're in opposite directions, and so work will be negative because cos 180 is -1. Now, in this waiter example, okay, where the force is going directly up and the displacement is going, in this case, to the left, then think about it. The cos of 90 is 0. So there is no work. The work is 0 here. F and D are at right angles. So there you go. So if the force and displacement are at 90 degrees to each other, the work done by the waiter on the tray is 0. A vertical force does no work on a horizontally displaced object. Okay, so when a force is exerted on an object at an angle to the horizontal, only a part of the force contributes to the horizontal displacement, the horizontal component. So that's why it's the scalar projection of the force onto the displacement vector. So in this example, Mariana is pulling a toboggan and exerts 40 newtons of force, acting 24 degrees to the ground. So how much work is done in 100 meters? So here she's going, okay, for 100 meters. But she's pulling it. Here's her actual force. And this is 24 degrees. So the work done is going to be the product of this ON times the 100 meters. So ON is 40 cos 24 degrees, which gives us 36.54 newtons. So that means out of this force, 36.54 of those 40 newtons are being done in the horizontal direction. Okay, so now work is just that 36.54 and being multiplied by the 100 meters displacement. Okay, so you get 3,654 joules. Okay, so that is how much work is done in 100 meters. Okay. So now we get on to an application of the cross product, which is not going to be intuitive to you, but if you want more information, I'll tell you where it is in the textbook. We don't need to actually go ahead and do this proof. But if we have a parallelogram, so I will call this A, B, C, D, and this is the height of parallelogram here. So let's say AB is a vector and AD is a vector. So we'll call this little vector A, we'll call this little vector B, like that, where theta is the angle between A and B. The area of this parallelogram is the magnitude of A times the height. And this can be rewritten as the magnitude of A, and then height can be rewritten as the magnitude of B times, sine theta. Okay, that's just rearranging SOHCAHTOA in this. So there is a proof that A, magnitude of A times magnitude of B times sine theta is actually the magnitude of the cross product between those two vectors. Crazy, I know. But if you want to go to page 411, there is the proof of how this is determined, if you don't believe me. AB sine theta is the magnitude of the cross product. So if you want to determine the area of a parallelogram determined by these two, we're going to just go ahead and do the cross product and then find the magnitude of that cross product. Okay, so remember we put the second one, the third one, the first one, and the second one, and then we do the second one, third one, first one, second one, and then we start doing our crosses. So you can watch the cross product video if you need a refresher on how to do that. But you get negative 23, 11, and negative 13 as your resulting cross product. So now we do the magnitude of that cross product. So that's the square root of negative 23 all squared plus 11 squared plus negative 13 squared. So that gives us approximately 28.62 units squared, or square units. Okay, so they can also ask you questions like determine the area of a triangle formed by A, B, and C. So what is different about this question? Well, first of all, they are asking for a triangle. And they're also asking it between these three vectors, not between just two vectors where, you know, their heads would be, or their tails would be at the origin. So let's think about what this looks like to kind of help us understand what's going on here. So we have A, which is at like -1, 2, 1. And then B, which is at -1, 0, 0. And then C, which is at 3, -1, 4. So I'm just kind of like eyeballing where these are just to get a visual. So we're going to form a triangle between AB and AC. So, and then here's the other side of the triangle. So this is half of the parallelogram formed by AB, vector AB, and vector AC. So if we can find the area of the parallelogram formed by AB and AC, we just cut that in half, and that is the area of this triangle. Okay, you could also do BA and BC or CA and CB. It doesn't matter. You just have to pick two vectors that would work. So I picked AB and AC. So we actually have to find AB and AC first. So remember, to find the coordinates of vector AB, you do OB minus OA. Okay, so you subtract. So B is -1, and then minus a -1, comma, 0 minus 2, comma, 0 minus 1. So AB is coordinate 0, -2, -1. And you can do a similar process to find AC, which would be 4, -3, -3. So now we cross AB with AC, okay? So you can set up your variables, do the whole cross product dealio, and you get -9, -4, 8. So then you find the magnitude of that cross product. So the square root of -9 squared plus -4 squared plus 8 squared, and that equals √161. So then the area of the triangle ABC is half of √161, which is approximately 6.34 units squared. All right. Okay, we have one last application, and that is called torque. So torque is a measure anytime we have a turning effect on an object. So one of the most classic examples is a wrench being moved around a nut to tighten it, or if you're pedaling a bicycle, the turning effect of the axis on moving the bicycle forward, or even something as simple as closing a door and it moving along the hinges, okay? So torque is the turning effect of a force, which we just call F, on a point M. So it is a measure of how much a force acting on an object causes that object to rotate. So the object rotates around an axis, the pivot point, which is labeled as O. Okay, we call the force F. The distance from the pivot point to the point where the force is acting is called the moment arm, and it is denoted R. The distance R is also a vector and points from the axis of rotation to the point where the force acts. So torque depends on two things. It depends how much force you're actually applying to the turning and how far away from the turning point you're actually applying the force. So are you close to the turning point or far away? So if we look at this, we can label this M, this N, and then it's moving the force. You can imagine like taking this and moving it down like this. So you're rotating it where M is like the pivot point. So here's the radius, and this is the force. So M is applied at N and rotates about M. So you can imagine there is the rotating point. Okay, so you might want to go ahead and go to page 413 and actually read this description. It might be better than trying to take in a verbal description of this because it is quite complicated. But basically what we can boil this down to is that the vector R, which is Mn, is the position vector of that radius, and torque is actually defined as R crossed with F. So this radius crossed with this force vector will actually give you, so the radius and the force together create a plane, and then the torque is what's perpendicular to that plane. So imagine like going into, like you're driving down the bolt into the piece of wood or something like that. So what we're mostly going to be calculating, what you're going to be asked to do here is just understand how to find the magnitude of torque, which is the absolute value of this cross product, which we learned is going to be the magnitude of the force times the length of the radius times sine theta. Okay, where theta is basically the angle at which the force is occurring. So just a few notes here. This radius has to be in meters to find torque properly. So if it's in centimeters, you have to change it to meters. And force is measured in newtons. So as a result, the magnitude of the torque will be in joules. Okay. So if you want to understand that formula more, again, like I said, you can go to page 413. I think that you'll get a better explanation reading it, or I can explain it to you, obviously, in person, but this is what you're going to be required to know mostly, is just this formula for the context of this course. So a 20 Newton force is applied to the end of a wrench that is 40 centimeters in length. So our magnitude of our force then is 20 newtons. And the magnitude of our R vector is 0.4 meters. This has to be in meters. Okay, and our theta is 60 degrees. The force is being applied at an angle of 60 degrees. So the magnitude of the torque is the magnitude of the cross product, which we learned is magnitude of F, magnitude of R, sine theta. So we just sub in our values, okay? Our force is 20. 20 times 0.4 times sine of 60 degrees. So you get 6.93 joules. Okay, there is one more important piece of information you'll need to be successful in these problem solving questions. So if you want to maximize the magnitude of torque, number one, the distance you are away should be as big as possible. So think about it, if you're closing a door, to get the most torque, you would want to close it not close to the hinges, but as far away along the door as you can. Or if you have a wrench, you want to be applying the force at the very end of the wrench to get the most torque, as opposed to, going right close to where it's actually turning. You don't want to do that. And we also want our sine theta to be as big as possible. So we want it to be 1, so therefore we want theta to be 90 degrees. So this means that the force should be applied at a right angle. So again, if you're thinking about closing a door, for example, you want to put your hand directly on the door and push, as opposed to like pushing kind of from a different angle. That will give you the most torque. Okay, so those are 3 important applications of the dot product and the cross product. Thanks for watching. Hope you learned lots.